B-18's liquid oxygen tank ripped open, methane tank deformed, and many called it a total failure. But SpaceX found something unexpected in the wreckage. The new V3 fuel transfer tube survived nearly intact, even at the explosion's origin point. The booster didn't collapse despite catastrophic tank damage. The forward section with hot staging hardware showed zero damage. What do these survival signs reveal about V3's true capabilities? Which upgrades prove their value even in destruction? And can SpaceX still hit that late January flight target? Let's dive right in. When engineers approached the torn-open booster, they expected to find shredded components everywhere. The fuel transfer tube, a massive pipeline running from the main tanks down to the engines, sits directly in the explosion zone. In V2 boosters, a tube this size would have been ripped apart like paper, but this wasn't V2 anymore. The V3 transfer tube survived nearly intact. Only a small puncture marked where the explosion originated, yet the tube held its shape and structural form. This component is scaled nearly identical to Falcon 9's proven design, allowing faster flip maneuvers and simultaneous engine starts during critical flight phases. How did a component at ground zero outlive the tanks surrounding it? SpaceX built this tube to function as the booster's backbone. The old design would have failed catastrophically under the same conditions. What we witnessed wasn't luck. It was over-engineering paying off in the most extreme test possible. This single survival tells engineers that the core propellant delivery system can handle stresses far beyond normal operations. B-18 should have collapsed. The liquid oxygen tank section was torn open, exposing internal structures never meant to be visible. The methane tank deformed along its outer shell, indicating severe internal stress. This damage occurred near the test tank region, where propellant loads during ground operations. If the vehicle had buckled, the surrounding structures and equipment would have faced catastrophic damage. Yet B-18 stood upright throughout the entire incident. Teams continued working around it safely, assessing damage and planning next steps. What structural improvements allowed a booster with massive tank failures to maintain vertical stability? Part of this resilience comes from V3's reinforced frame layout. Part of it stems from that upgraded transfer tube acting as central support. This stability is critical because V3 will handle missions requiring higher reliability, orbital insertion, payload delivery, and precision landing operations. A stronger foundation at the booster level means SpaceX can focus development resources on the second stage, where the most advanced tasks occur. The forward section told another story. Hot staging hardware, integrated grid fins, and critical navigation systems showed zero damage. This region sits far from the explosion point, but distance alone doesn't explain it. SpaceX clearly reinforced this area. Essential operations during stage separation and the precision maneuvers required for catch attempts. When those catch arms close around a returning booster, the grid fin area must maintain perfect structural integrity. SpaceX made one decision that prevented disaster from becoming catastrophe. They chose structural stress testing before cryogenic propellant testing. This fuel-free evaluation exposed the weakness without introducing the variables that create uncontrollable fires. If they'd rushed to cryogenic testing during the previous window, we'd be discussing a very different outcome. Liquid methane and oxygen under pressure, combined with structural failure, creates conditions far more dangerous than what actually occurred. The fire would have been larger, hotter, and nearly impossible to control. How much worse would the damage have been with fully loaded tanks? These fuel-free evaluations rarely get attention because they lack the dramatic visuals of cryogenic tests. No frost coating the tanks, no venting vapors, no countdown sequences. But this incident proved their value conclusively. Finding critical flaws before introducing propellant isn't just smart, it's the difference between learning and catastrophe. The fuel tanks remain vulnerable. Cryogenic propellants create enormous pressure and temperature stresses. These tanks need additional strengthening through protective layers or redesigned welds. Without these improvements, leaks and structural weaknesses will continue threatening missions. The internal plumbing system demands equal attention. These pipes carry fuel and oxidizer throughout the vehicle like blood vessels in a body. Cracks, blockages, or stress fractures in any single line can compromise entire missions. At Starship's scale, maintaining these systems becomes exponentially more challenging. Every valve, connector, and line must handle repeated flights without degradation. The engine compartment faces major changes. Super Heavy will carry 33 Raptor 3 engines, each producing 280 tons of thrust at sea level. That's over 9,000 tons of combined thrust at liftoff, nearly 3 times Saturn V's power. But Raptor 3 isn't just more powerful, it's fundamentally simpler. SpaceX removed the small, delicate components that plagued Raptor 1 and 2. The new design merges complex assemblies into larger, integrated units. This simplification eliminates failure points. No tiny parts to trap heat, no narrow channels to leak, no fragile bolts to crack under stress. Can an engine this powerful really be more reliable through simplification? The answer is already appearing in manufacturing rates. Raptor 2 reached 1 engine per day. Raptor 3's streamlined design could achieve several engines daily, supporting rapid prototype construction. After landing, simpler engines inspect faster, maintain easier, and refurbish quicker. This brings SpaceX closer to fully rapid and repeatable launches. While Super Heavy grabs headlines with raw thrust numbers, the ship faces equally demanding challenges. Its vacuum Raptors must perform flawlessly in space's harsh conditions, handling orbital maneuvers and controlled re-entry. Several V2 flights experienced engine failures that resulted in loss of control. V3 cannot repeat these issues. The heat shield received major refinements across S-39's visible sections. Tiles installed with greater precision, tighter spacing, and consistent structural layout. SpaceX no longer plans to remove large tile sections between flights because V3 moves toward operational readiness rather than pure experimentation. Engineers updated tile materials and ratios to prevent cracking and chipping. The crunch wrap technique from Flight 11 received further optimization to fill gaps between tiles and underlying structure, blocking heat intrusion that threatens internal systems. Metallic tiles were removed after tests revealed potential oxidation from cooling fluid leaks. Why does tile survival matter more now than in V2's experimental phase? Because V3 carries the expectation of rapid turnaround and partial or full reuse. The heat shield must withstand extreme re-entry temperatures while remaining in condition, allowing fast refurbishment. This level of reliability on such a massive system requires ongoing focus from engineering teams. S-39 revealed something unexpected when it moved for stacking. A new refilling point positioned just beneath the payload door. Currently, it's just an empty structural cutout with no internal hardware installed. This isn't the final version. It's a test article, giving SpaceX the chance to study how the interface performs under real flight conditions. The results from these tests will shape refinement and eventual full integration. Reports suggest first operational demonstrations may occur around June, marking a major milestone. Why does this seemingly small addition matter so much? Because in-orbit refilling unlocks everything. Deep space missions, heavy payload deliveries, crewed journeys far beyond Earth orbit, all depend on the ability to transfer propellant between vehicles in space. Without refilling, Starship's capabilities remain limited to what a single launch can achieve. With refilling, the entire solar system becomes accessible. S-39 should complete its full stack soon, moving into detailed inspection before heading to the Massey test site. Stress testing comes first, ensuring the ship can endure structural strain before any cryogenic propellant enters the tanks. After stress tests pass, cryogenic testing pushes tanks and plumbing to their limits under freezing conditions. If everything performs as expected, S-39 returns to Mega Bay 2 to receive its engines. Then comes the static fire test, the first time Raptor 3 engines deliver full power demonstration on a flight-ready ship. If the schedule holds, S-39's work wraps before December ends. B-19 progresses slightly behind. Stacking should complete mid to late December, with cryogenic testing near month's end or early in the new year. After B-19 completes its tests, it moves back to Mega Bay for engine installation. Shortly after, we may witness over 9,000 tons of thrust firing up for the first time. This milestone could occur as early as mid-January. With this pace, Flight 12 appears possible in late January or early February. If successful, it prevents major disruptions to next year's development goals. Can SpaceX maintain this aggressive timeline after the B-18 setback? SpaceX has pushed through a challenging year. Both stages encountered significant setbacks and progress naturally slowed. Yet the company keeps turning obstacles into forward motion. The B-18 incident could have been catastrophic, a fuel-filled explosion destroying equipment, delaying the program for months, maybe forcing a complete V3 redesign. Instead, what happened? The transfer tube survived at ground zero. The booster stood upright despite torn tanks. The forward section showed zero damage. Critical systems proved they could endure conditions far beyond normal operations. And most importantly, the problems were caught before flight. Early discovery is invaluable. It leads to safer, more reliable missions. We saw this pattern after the first V2 flights and the S-36 incident when SpaceX closed the year with 2 successful launches. History suggests a strong rebound is coming. The first V3 flight won't just debut new hardware. It'll mark a powerful return, the next leap in the Starship program. Version 3 carries upgrades that reshape how this vehicle performs. From the simplified Raptor 3 engines producing over 9,000 tons of thrust to the integrated grid fins, reinforced structure, and in-orbit refilling capabilities that unlock deep space missions. Challenges aren't failures. They're lessons, data, and the fuel-driving improvement. The V3 era is here, and the momentum is building. What's your take on V3's survival signs? Which upgrade impressed you most? Drop your thoughts in the comments below. If this breakdown gave you new perspective on the B-18 incident, hit that like button and share it with fellow space fans. And subscribe to Space Update 24 hours so you don't miss what happens when B-19 fires up over 9,000 tons of thrust for the first time. That moment is coming soon.